We're very happy to have Volker Schomerus from DAISY coming here for the HMI advisory board meeting and in parallel giving this lecture. Volker is an old friend. He's been here, whatever, 15 years ago, probably 20 maybe years ago. But this is a new building, okay? And it is 20 years of creation, at least in my mind, of this Hamilton Mathematics Institute. So there is a double celebration, and it's very appropriate that we have the friends who celebrate with us. So Volker, thank you so much. This is a very modern topic, so we will see what integrability of integrals means.
Okay, good. Thanks a lot.
Integrability of integrals.
Right. Thanks a lot for the invitation. It's always a pleasure to come here. And indeed, I have been, I think, over the course of this last 20 years, been here many times. In fact, it feels like one of the places I visit the most in the world. So and that's, I think, mostly due to you insisting that I actually come in person. Anyway, it's a great pleasure to be here. And as you can see, this style will be completely different from the previous talks. And I want you, I mean, either you just enjoy and relax and fall asleep, or you ask lots of questions to try to understand what I'm going to talk about. So so this talk is about an important subject, namely computing correlation functions of, let's say, local field in the quantum field theory. Okay, so you imagine you have some kind of local fields, and of course, as you all know, it's very difficult usually to compute such correlation functions. So you usually do this in a perturbative expansion, unless you can solve the theory exactly, and then you write down lots of integrals and spend your life, maybe not you, but some people in this world spend their life computing these integrals, and then eventually they get formulas for these quantities. So today, so in fact, one common strategy is basically you have this decomposition and you try to decompose these correlation functions, so write it in the sum of things that you can control very well, right? With maybe some coefficients that you can then compute. And so the main message of today's talk is that for a certain class of integrals, I'll show you sort of a way of writing them as a sum of computable integrals. In fact, integrals that have the interpretation as being wave functions of some integral system with coefficients which are just rational in the parameters of the theory. So, so my general introduction, I mean, again, in principle, there's integrability probably in many integrals that appear. So first of all, I should say this is in, as I said, it's in conformal field theory. Of course, in the last 20 years, many people have studied conformal field theory, in particular since ADS-CFT. It's a very important topic. And so whenever you do computation in a conformal field theory in D dimensions, you meet tons of integrals, conformal and variant integrals that you have to compute. Now I will actually from the very beginning go to the to those theories that have an ADS dual. So so it's according to the ADS-CFT correspondence, certain gauge theories in the planar limit, when you set the number of colors to infinity, possess a dual description at strong coupling, which is given by a classical gravity theory in ADS, in one-dimension higher anti-de-Sitter space. And so there's lots of elements what this equivalence means. So first of all, what you can see is that, of course, the symmetries match if you have a conformal field theory. So the conformal field theory lives on the boundary of this ADS space. And so the conformal group, Euclidean Lorentzian conformal group is SO2, D, and that's also the isometry group of ADS space. So the symmetries match, and then you have entries like when you have in your conformal field theory some kind of scalar primary field of conformal wave delta. It corresponds to in ADS to some massive Klein coordinate field with a mass which is determined by the dimension of the field in the CFT. Or the stress tensor in your CFT, and in the CFT you have such a stress tensor that corresponds to a massless graviton, that property is ADS. Now, then soon after formulation of this ADS-CFT correspondence, Witten describe how you compute correlation functions. So now you want to compute correlation functions, let's say some local fields, but you want to do that at strong coupling where your ADS CFT duality works like easiest, just in terms of supergravity. And so the prescription, I'm not going to explain, of course, in detail. Many of you know the prescription by heart, and others probably won't learn it from this talk, but I just want to give you the flavor of what you have to do.
May I ask
Yes.
a naive question by a mathematician?
Yes.
How is the correlation function defined in this context? As a definition.
So let's say maybe I can take this as a definition here.
This formula.
This formula. Okay, so I think this formula is relatively precise if you understand what it encodes. So it's you imagine somehow that you have a bunch of fields inserted at some points on the boundary of ADS, and you want to associate some kind of function to this, and that's what we call correlation function. So Witten's prescription is the following. So you actually okay, I guess no, I take that back. So of course I'm just describing here contributions to the correlation function. I could
Well, let's say this way, you have to take a course on quantum field theory. Right. Even that,
For a definition.
so
even that is not, even that is not.
yeah.
So,
But I mean, for it's a sum of terms, but of course, without giving a definition, you cannot even decide which terms to include or not to include. But you can think of it, I mean, I don't know, really background. For me, it's enough if you think of some kind of infinite-dimensional integral, half integral. So
In 2 dimensions, you can define.
in 2 dimensions, I can define. So, okay, as Samson says, you need a course. I'm happy to give the course after this.
Can you do it for instead of me? I'm teaching.
Okay. Why not?
Why not? Yeah. Next year.
So this quantity is the correlation function. So the prescription of Witten was that you can actually compute this by through a sum of integrals. You kind of draw like pictures like this with various elements. So there's kind of propagators that move from the boundary into the bulk, and then there's some bulk points here, vertices, and then you have propagators in the bulk.
This is the one that he got from CP3/3, right?
No, this is just the strong coupling. I mean, this is
When he wrote n equal 4 in terms of
97.
check size.
No, even before. This was in 97, just a few months after Modafena
The first paper.
had written this paper on ADS CFT. This was sort of one of the more important parts of the dictionary because it made really precise how you would actually compute a correlation function with strong coupling. So the prescription is basically that you need some elements here. So you have a propagator that describes sort of the bulk-to-boundary propagator. That's some very concrete function. So the argument of this function is basically some coordinates here in your bulk and the coordinate on the boundary, and then you have some concrete function like this, and then you have the bulk-to-bulk propagator. This is just a Green's function for the wave equation on ADS with some mass. So I gave you here, just for reference, a solution for the massive Klein-Gordon field in ADS. That's what the propagator looks like. So you put all these things together, these bulk-to-boundary propagators, which go from x to some point y, then the bulk-to-bulk propagators, which go like this, from y to y prime, and then in the end, you multiply all these things. So in this case, here would be 6 of these bulk-to-boundary propagators, 3 of the bulk-to-bulk propagators, and then you would perform here 4 integrations over all the vertices, okay? And so that's an example of such an integral. So now you can put all these things together, plug it in the integrand, and try to compute this.
Is that just one contribution?
This is only one contribution. Again,
Infinite sum.
well, at 3 level, there's some finite sum of terms that you have to actually compute. So anyway, it's a complicated calculation, and people have done this in the first few years after 97. They computed such things. So then a few years back, in 2015, in this paper by these authors up there, people noticed the following thing. You can actually modify, so I've now simplified the picture a little bit. So this is now An integral corresponds, this picture corresponds to an integral with 4 of these boundary propagators and some bulk propagator, a single one inserted, and this would be an integration here over 2 bulk points. So the initial integration for the Witten integral would go over all ADS space. But so what these people proposed is just to integrate these y and y prime over the geodesic that goes from this insertion point to that insertion point, and another geodesic that goes from here to there. Okay, they're called geodesic Witten integral. And so that's a funny prescription. But what's nice about it, so the
Equal to the Witten sum?
no, it's not. Of course not. So it's not. So I will describe the relation. So so this integral, of course, is conformally invariant, right? Because you've integrated over all of ADS, and ADS has isometry, the conformal group, so it's a conformal invariant. And the nice thing about this prescription to just integrate over these geodesics is that it's also conformal invariant. And the way for you to understand that is that, of course, if you act with your conformal symmetry on these points, the geodesics, of course, are also transformed by conformal symmetry, right? So so if you restrict your integration over these geodesics, it's still a conformal invariant. Of course, it's a different assumption. Both, it's not no reason to believe it's the same object. In fact, these integrals, when you just integrate over the geodesics, they have additional properties. So what you can check is that they satisfy extra differential equations that the original integral does not satisfy. Okay. So one way to see that is if you act here with the conformal symmetry, let's say on these 2 points, right? Then you will move your geodesics, and somehow you will get an action of the Laplace operator on this propagator. And so the propagator is sort of an eigenfunction of the Laplace operator. So you'll actually get an eigenfunction if you act here with the like the Casimir operator that corresponds to acting on these 2 points simultaneously. This function will be an eigenfunction of the Laplace operator. Okay.
So you're integrating over the exchange part.
So
you're including the bulk to bulk.
Yeah. It's the same. The integrand is the same. You just change what you.
Is it like taking an iconal limit or something? Is it like taking an iconal limit? If the external particles are very, the exchange is very small.
So this is a different quantity, right? I mean, it's
Okay, so wait. There is some formula here defined as an integral like that satisfies differential equation. This Casimir acting on that. It has many solutions.
Right. Well, we'll talk about the solutions of these differential.
But where is the simplification?
Well, the nice thing is
because Tristan proposed it's an econal approximation.
No.
It looks like
so what they then proved is, so that addresses Samson's question, that the initial Witten integral can be written as a sum of these so-called geodesic Witten integrals with the coefficients that were very, very simple coefficients. So it's a discrete sum over, it's an infinite discrete sum, but the coefficients are just all rational in the weights of the fields, okay? And you can write down a closed formula for all the coefficients, for every single coefficient, okay?
By the way, excuse me,
Yeah.
I would think that the original integral in previous page also satisfies differential equation, which is consequence of conformal world identity.
Sure. Of course, but that's as we will see. This is that's true. It satisfies.
So I would say both.
But that just tells you. So let's say in 4 dimensions, there's 15 conformal water identities. So it will reduce the complexity of this function. But if you are, let's say, if you compute a 4-point function in 4 dimensions, you have 16 x's, and then when you impose conformal water identities, you still have a function of 2 cross ratios.
So we solve that one also. It satisfies Casimir.
Yeah.
But there are
I agree.
I'm trying to figure out where is the simplification.
Right. So the simplification is, so that's the story that I'm going to tell you, is that these integrals are actually they're as I said, they solve some differential equations, and these are differential equations that come from the eigenvalue equations of some integral system. So these are actually wave functions. These objects here you can think of as wave functions of some integral system. In fact, it's a Boudin integral system in some particular limit.
But
I'm going to show you.
because we know the answer to that.
Okay, good. So if you Yeah, so in some sense, yes.
Is it for SU2 or?
No, this is
compact,
non-
compact.
I think this is non-compact, right? I mean, this is a conformal
PSL,
group.
PSL for
Okay,
four.
okay, good. Don't jump in. And you,
Can I ask,
Yeah.
when you say these type of objects, is it 4-point objects or arbitrary endpoints?
okay, so what I described here in this initial paper was written for 4-point function. The story, the analog story for higher points is not understood.
And it's always one exchange or multi-exchange?
So here you go. So I mean, typically, of course, the 4-point function and the strong coupling limit
It's just one line.
you would have several such diagrams, right? That you could write. I mean, there's S-channel and T-channel exchange and contact diagram, but all of them actually can be expressed in terms of the same types of geodesic Witten diagrams, and always you can give closed formulas for the coefficients.
It's always tree level. You're not looking at
Well, you can also look at loop, but right now the statement is about tree level. Okay. So, but in the sense of my initial question, somehow this formula solves the problem, in the sense that, I mean, you can compute the initial diagrams in the sense that you relate them to these special geodesic Witten diagrams. So if you are able to compute the geodesic Witten diagrams, then you have a formula for the forwards. Okay. So and so my discussion will be about these objects, these building blocks. Yeah.
Is there an explanation why this should be true or just empirical observation?
Yeah. So there's an explanation. I don't want it. So it's actually not so difficult to understand that this works. I mean, so these coefficients are very simple to calculate. There's a simple formula for a product of these boundary propagators that allows you to just compute that. So it's I didn't really offer much explanation. I understand that this is so simple, but there's a deeper understanding of why this should be true. So the upshot of this paper is, in some sense, when you go to compute these Witten diagrams, to compute correlation functions of strongly coupled conformal field theories in the planar limit, the problem of computing these integrals is down to computing these geodesic integrals, and that is conformal invariance, which satisfy a certain set of Casimir differential equations, higher order Casimir differential equations. Okay, and so I will now turn to the calculation of these pieces. So first of all, I wanted to give you a precise formulation of our task. I mean, this was so far sort of a bit in the physics realm. So now I will try to describe what these objects are actually, so in a more mathematical formulation, so that we can identify them very clearly. Once that is achieved, I will talk about how you can understand them as wave functions of some integrable system, and I will answer the question which integrable system precisely that is. And then I give you some examples and also show you the realm of the things that have been actually computed.
So this is connected to the talk that you gave here before COVID about the Gmod H for conformal group and.
Yeah, it's related to that. I mean,
that's Zachenko, I think you had the paper.
Right. So that was an early one that was just dealing with sort of the 4-point function. Our story is more general.
So this is continuation of that kind of stuff?
It's a continuation of that kind of stuff. Right.
I understand things only historically, how I just developed. Sorry.
Right. Yeah. And of course, I tried to hide this by now taking everything around, but good. So I'll come in the end of this. That will be special example. The scope is much wider. Okay, so again, I go through this quickly. Again, the task of the next 10 minutes or so is to just give you sort of a more precise mathematical formulation of what we are trying to achieve. Okay, so and then you can forget in principle everything that I told you before about motivation and correlation functions. So first of all, let me remind you. So now we switch signature. That doesn't really matter. We go to the Euclidean conformal group. It's SO1, D plus 1. And just so that everybody's on the same page, it's of course a Lie group, right? It has a bunch of generators, and physicists have nice names for them because it's a conformal group. So we have an SOD Lie algebra that generates infinitesimal rotations of your d-dimensional Euclidean space. You have translations in there, and then dilations, scale transformations. And finally, special conformal transformations, as a vector of special conformal transformations. And you can write down, of course, the Lie bracket for all these things. So the special thing is somehow you have some degree 0 generators, rotations and dilations, and then you have some raising guys that create, in some sense, are represented as derivatives, and some annihilation guys, these special conformal transformations. All of them act on the RD. In fact, that they act on RD, on the d-dimensional Euclidean space, is something that you can understand quite easily. When you think of the stabilizer subgroup of a point, so if you take a point, let's take the origin of our Euclidean RD, right? Then rotations leave that point invariant. Obviously, translations don't, but rotations leave it invariant. Special conformal transformations can be thought of as translations at infinity. They also leave this point invariant, and dilations leave that point invariant. So the stabilizer group of a point in RD is this particular it should be a semi-direct product of the conformal group generated by special conformal transformations, rotations and dilations. And the quotient of the conformal group by this subgroup is RD, or is a d-dimensional space. So, and of course, on the quotient, you have an action of the conformal group, right? Because this is just the right quotient. So there's obviously this quotient is a space on which the conformal group acts, and that's sort of the action of global conformal transformations on this d-dimensional space. So now the physicists have the notion of a primary field. That was something that lived on the boundary. That's a field in your quantum field theory, and it's characterized by the way the conformal generators act on that. So we say we have a conformal field, primary field of dimension or conformal weight delta and spin sigma if the field satisfies the following type of relations. Now this is easy to understand if you look at this, and with the more mathematically trained eye in this audience, I think I don't have to do much of that. So suppose you pick some representation of the rotation group, that's what physicists call spin, and some representation of dilation group, that's what's called the weight. Then of course this induces a representation of this semi-direct product here with by just extending it trivially to the special conformal transformations. So spin, lambda, and weight give a representation of the stabilizer group. And then what happens here is basically you induce now a representation of the conformal group in the following way. You take all functions on the conformal group, SO1, d plus 1, into some representation space, finite dimensional representation space, on which you can particularly realize this spin representation of SOD. The representation of SOD, it could be vector representation, symmetric traceless tensors, whatever you want. And you impose these covariance conditions that when you multiply from the right with some element of the stabilizer group, that the function transforms covariantly by kind of rotating the image if it's taking values in the representation of the stabilizer group. So this is bonified. And so you can think of this as roughly giving you so this gives a representation. It's a construction of a representation of the conformal group, right? Because this space here is a linear space of functions on the group with these covariance properties, carries, of course, an action of the conformal group on it, because you can now act with the conformal group from the left, and you get a representation of the conformal group. And this is a way to build irreducible representation of the conformal group. For instance, you can build principal continuous series representations of the conformal group in this way by choosing delta to be d over 2 plus I times some real number. Okay, so this way you build representation of the conformal group, and when you look at these representations, then you can see that this is basically what these relations of the primary field tell you.
Actually,
yeah,
it's probably last time I asked you also. It's also that question I'm going to ask also appears in the case of Cadet. So you are now decomposing into the you take representations, and you probably then will tell us that now I'm calculating correlation functions which of operators which are labeled by these guys and so on. But this is non-compact group. And for example, if you try to do SL2C Gaden model, which is similar thing, you take operators, you multiply. So in the product, there is no invariant. So when you are talking about continuous series representations, you multiply them. Normally for SU2, you will take 3 points or 4 points, and now you have this thing and you say this is invariant of this group and so on, and it works. But in this case, exactly like for SL2C, 3-chain or SL2C Godin, there is no invariant in the problem. How are you going to handle it? Yeah.
Let's defer that. We will come back.
But you answered it.
Yeah.
You will answer.
I will.
Okay.
Good. So that was like the one thing. So the primary field now replaced. I will not talk about primary fields again. I will just talk about representations of the conformal group, and I constructed them as functions, realized and realized functions on the conformal group itself, and I think that's it's easy to kind of understand. So now, So now the next thing is this this notion of invariance, conformal invariance of this block. So these generators here, these T with index alpha, these are the generators of the conformal group, and there is a representation for each of the, like I said, I won't talk about primary fields again, but for each of the primary fields, there is a representation. So what these curly T would be these expressions here, some differential operators, concrete differential operators acting on the axis. And conformal invariance or semi-invariance means that that these objects here have to satisfy what's called conformal water identities, which is a set of linear differential equations, simple linear differential, first order differential equations that are just obtained by summing over the action of these differential operators over all the different points. Okay. So these are as many differential equations as you have generated in SO1, comma D plus 1. Sometimes they are not all independent. If you have a small number of points, there can be some dependence between those things, but that's a minor point. That's this statement about invariance. So, or semi-invariance, I should say, because these things are not invariance, as you will see from here. So also people working in conformal field theory, of course, know very well that if you use these water identities and try to say something about 3-point blocks, functions that depend on 3 fields, then you can actually completely fix, up to normalization, you can completely fix this object. If these 3 fields are scalar fields. The sigma on the previous slide, the sigma here was 0. You had the trivial representation of rotation group. You can completely compute these 3-point functions. And here's the formula. And of course, the reason that you can do that is that if you have 3 points in your d-dimensional space with conformal transformations, you can move 1 to 0, that's translations, 1 to infinity, that's special conformal transformations, and then you have rotations and dilations to move the next one on the line from here to there to infinity at point 1, so where Samson sits. And so there's nothing that it cannot depend. The quantity that is satisfies these water identities and only depends on 3 axes, cannot possibly depend on anything. And this funny behavior here that it depends on these differences of the axes with these exponents, of course, that comes from the fact that it's not just 1, comes from the fact that these expressions here have these deltas. All right, so you can do the same thing. So I use the following symbol now for this function. Okay, that's so the next thing is you can do something like this also when this the third field is not a scalar field but a symmetric traceless tensor field of spin L. That means you have a particular representation. I mean, the sigma here is now a non-trivial matrix, right? Corresponding to like if it's a vector, it would be a d-dimensional representation. And you can also work out the same argument. You can work out this function. Okay, and there's formulas for that, which I'm not going to give you. You just see the symbol here. That means some concrete function. Now, one thing I should maybe say is that if you have more than one of these symmetric traceless tensors, then this argument doesn't work anymore. And you can actually check that there's not enough water identities to completely fix the 3-point function. And instead you have sort of a finite set of objects of this type, a finite set of functions that like span the space of invariants. Okay, and one way to understand that is, let's say, again, let's go to 4 dimensions. In 4 dimensions, conformal group has 15 generators. Okay, so 6 rotations, 1 dilation, 3 translations, 3 special conformal transformations. Now, in a generic representation, so the P's, the 4 translations, they're always sort of raising operators in the representations, right? And in the generic representation, you also have the 6-dimensional rotation group in 4-dimensional space. There's also 2 creation operators, 2 upper triangular operators. There's 2 annihilation operators and 2 on the carta. Okay, so generic representation somehow has 6 creation operators. Okay, whereas the scalar representation, where you have no creation with rotation, has only 4 creation operators. So in this thing, we have 6 creation operators to build sort of in this representation, build these representations associated to the to spin L. 6 here, that's 12, plus a 4 here, that's 16. Okay, 16 creation operators, but the conformal group only has 15 generators, so you cannot completely determine these objects by the ordinalities. And so there's a finite number of solutions. Okay, and the finite number is actually, it's finite for any given choice of spin, but if the spin becomes very large, then this actually becomes infinite. So the number is given by the minimum of the 2 spins. All right. So so that was on the 3-point function. Now let's come back to the last property that we want to require. We want to require that our objects that we're looking for, these blocks, satisfy certain higher order differential equations. I motivated that here from this picture. This is a property that this geodesic Witten diagrams have that were introduced. And so the type of equations that we get now is that we take a Casimir operator, let's say order Q Casimir operator, that acts on these 2 points here. And so this is a differential operator that you can, of course, work out from the formula that I gave you, right? You take just the T1 plus T2, the action on X1, action on X2 is a concrete operator. You take the square, let's say, and then you get a quadratic Casimir, concrete second order differential operator, if you do that for the quadratic Casimir. And the objects that we're looking for, they're supposed to have this property that they're eigenfunctions of these higher order differential operators with some eigenvalues that are given by the values of the Casimirs in some irreducible representation.
So you assume that all these phi's are having their own delta and L, or many of
So
them
the
are
phi's,
scalars and only one has.
so well, now I can go back if you want to having these phi's are all scalars, but of course in this intermediate channel you can have fields which have non-trivial L, right?
But outside phi's are scalars.
Let's say, again, for simplicity, I can use these scalars. I mean, that was the case that I considered in the but I don't have to. Okay. So we have, so we are now looking for objects. So now that's a sort of our complete list of what we want, right? We're looking for objects, these psi's, which are functions of x1 to xn, let's say. They are, these x's carry weight delta 1 to delta n. They should satisfy these linear ordered entities, so these first order differential equations, and then a set of higher order differential equations. And these higher order differential equations, in fact, as you see, they make reference to some particular what is called a channel. So here I chose, for instance, the action of the operator on x1 and x2, and then this object was an eigenfunction of this operator. It cannot be simultaneously also an eigenfunction of the operator that acts on 2 and 3. Okay, so you make a reference to the choice of what is called a channel, and for any given channel, so we'll see examples in a moment, you have a set of differential equations that you want to be satisfied, high order differential equations. And so the claim is that that this is giving rise to a nice problem. So in the case of these 4-point invariants. In fact, these differential equations that I have that come from, let's say, second and fourth order Casimir are already sufficient to completely fix the function. Okay, and in fact, as we'll see later on, these are very famous differential equations that have been solved in a very different context about 30 years ago, maybe 40 years ago. But in general, they have not been solved. All right, I think I can leave this this out. So, okay, so now I hope in the last 10 minutes or so I explained to you what the mathematical formulation of the problem is that we have. So we're looking for functions with these properties: set of linear differential equations, set of higher order differential equations which are associated to the choice of one of these of a channel.
You promised me to answer when we take tensor product of different representations, and we're looking to you. So all these things to be invariant. We're picking the invariant or not under the action of the conformal because
Yeah.
we promised.
Yeah, I will.
Not yet.
All right, good. So, you like?
You have 5 minutes.
Yeah, I know. You're pushing.
No, it was
Good. All right. So here's our task. We're looking for these objects psi, which depend, of course, on. When I write this psi, you see the psi is now different from the psi in the previous slide. So I've kind of assumed that I've implemented these linear differential equations already because they're just linear equations. So that's relatively easy to take into account. And that means that these functions do no longer depend on the axis, but they depend on conformal invariant cross ratios. So if we do this for a 4-point function, they will only depend on the two cross ratios u and v. If I do it for a higher point function, you just have to count the number of cross ratios, and then you will know how many variables there are. So we want to construct a complete basis of functions, and so we need sort of these functions to be enumerated or labeled by quantum numbers, and there have to be as many quantum numbers roughly as there are variables here. So for instance, in the 4-point case, we have two cross ratios u and v, and we have also two quantum numbers, namely delta and L, of the intermediate exchange fields. So Casimir eigenvalues of the second and fourth order Casimir. And they depend on the choice of this channel, because if I take 4 points, I have this choice whether I want to diagonalize, for instance, the Casimir operator C1, 2 or C2, 3. Okay. So what we're trying to look is for each choice of channel, we look for a complete basis of eigenfunctions. Or functions with which you can expand our integrals. And so now here I have a long list of examples, maybe that I won't go through in detail. So we have seen 4-point functions already, right? 4-point functions, we have two cross ratios and also two labels for the intermediate field. So the intermediate representation, the second and fourth order Casimir are independent, while higher order Casimirs, if they exist, they will be dependent of that. For instance, if you want to construct a 5-point function, then you have to first count how many cross ratios there are. And so we counted like the two cross ratios before. For the 4-point function, this was the fourth point, right? We had these points on the line here where I am and where Samson is, and then infinity. And then the fourth point by rotations, we can move it by SOD minus 1 rotation, we can move it into the floor, let's say. But if we have another point, a fifth point, then of course we have only SOD minus 2 rotations left. So we have to move that somewhere into 3 space. But so if we're in 4 space, we cannot really simplify it anymore. So this is only to say that you have 5 cross ratios that you can build out of 5 points in any space that is larger than dimension 3, larger equal than dimension 3. And in this case, there's also 5 labels attached, right? You have these Casimir eigenvalues of the intermediate fields, and then this label n that I discussed before, because now you have a vertex here that is more general. It has 2 sort of spinning legs, and so that has its own quantum numbers attached to it. Okay, and indeed, the number of cross ratios matches the number of quantum numbers. So now you can look at the 6-point function. So who can tell me the number of cross ratios of the 6-point function? Okay, so it's 9 cross ratios in general if you're in dimension 4 or higher, and 3 dimension if you're only 8. And there's of course the same number of labels on it. Now you can have in dimension 4 and higher, you can have you can have mixed symmetry tensors. So there's the rotation group in four dimensions, of course, there's two Cartan generators, so there's two labels for geometric representation. Or if you took like a picture like this, it's just a different channel. In this case, you can have different channel topology. You can have 9 cross ratios, and you have, of course, 9 labels. But now the labels are different. So there's 3 labels that are just spin and dimension. So these are just 3 integers, and then there's 3 integers actually attached to this vertex. Okay, and this 3 you can also count from the rules that I gave you before. Now we have 3 generic representation. You remember each generic representation has 6 creation operators. 6 times 3 is 18, minus 15 is 3. So that's these 3. But always the number of cross ratios, the number of quantum numbers sort of matches in this picture. And so our task now is to somehow construct again this function, the full basis of these functions, and so that we can actually construct all these conformal integrals. All right, so now I'm going to show you how you can actually do this, and this problem actually maps to a problem in integrable systems. So my main claim is that these functions that we're looking for, these plies, they can actually be interpreted as wave functions of a quantum integrable system. And the Casimir operators, again, the Casimir operators that measure these quantum numbers here, they can be completed into a larger set of operators, including those that measure sort of these n quantum numbers, so that you have basically a complete commuting set of Hamiltonians, one for each variable or each quantum number, and can then uniquely construct these wave functions. And so there's a machinery that does that for you, is called, that's the Godin model. So in the Godin model, you have what's called a Lex connection. So this is just a family of matrix valued first order differential operators that act on your xi's, let's say. So the prescription here is the following. You take just standard representations of the conformal group. Think of the fundamental representations. I really does 6 by 6 matrices if you're in 4D. Then here, these are the differential operators that act on the describe the action of the first order differential operators. And below, you have a function of what's called spectral parameter omega, and you introduce some other complex parameters which you call continuity or the sites of the Godin model, obviously distinguished as poles. And to WJ, there's some complex set of complex number, one for each particle, each field in the FEF. And so you can reduce this so-called Lex connection. And then the magic is when you take any invariant of your Lie algebra, let's say the Casimir, the killing form or some higher invariant, and then you take these first order differential operators here. So I split off the matrix part, and you multiply this. So this is of course an acute order differential operator here, and summed over with this with the invariants. Plus you have to add some lower order terms, which there's prescriptions for that. Then the magic claim is that that this actually gives commuting differential operators, the family of commuting differential operators. So you can check that all these things, even though of course these L's here don't commute, right? They're complicated operators, first order operators. When you build these type of combinations, they actually commute. Okay, that's a pretty amazing fact. And on top of that, they also commute with these the total, I mean, action of the conformal group on the fields. So these combinations of generators that were now awarded in these invariance conditions. And so in this way, you get a quantum integrable system on some on the reduced phase space of this. Because they commute with rewarded entities, you can actually take this commuting family of differential higher order differential operators, and it gives you a commuting family of differential operators on this space of G invariant objects. All right, so good. So that's nice. So that's of course an old famous construction that was long known
For compact case,
for
compact group only. What they did, taking characteristics.
That's true, but the fact that you get sufficiently many independent
Yeah, but it's kind of I mean, this is the big question. The defense SU2, I take SL2R or SL2C, whether this actually can work out. Because
Well, you can check that you get enough.
one thing is,
I mean, this is
one thing is finite dimensional representation, another is infinite dimensional. SL2R has infinite dimensional representation. I'm multiplying them and asking, is there invariant under G? And then you work out, and you know it's complicated and it doesn't exist, and you have to put some other L2 conditions. So in Golden model, when you take 4 points on the sphere, condition instead of the invariance under the group, you're putting other analytic conditions for non-compactable SL2C. This is important.
sorry that I will come to this.
You see what I mean? You're not putting the Feynman-Krenkel conditions for monodromy.
I understand that this is
Yeah.
but for the, I mean, again, you get even the non-compact case, you get enough commuting objects.
That's correct, but it's abstract. When you start working on it,
I understand.
we should spend time.
That's why I tell you,
Yeah.
wait for the last part when I make it good. This is abstract.
No, I'm not interrupting you. I'm just trying to follow.
Yeah,
the thought.
sure. No, that's
Sorry, I just want to see where.
You will get two more slides on the abstract part and then I will.
Okay.
So, good. So this construction, of course, is good. That gives you differential operators on roughly the correct space of these conformal semi-invariants. And they commute all with each other. But the problem is, of course, we wanted some very particular operators. Remember, these geodesic Witten diagrams were diagonalizing a particular set of Casimir operators. And so now we have to somehow make sure that we find these Casimir operators. And so that actually requires to take these, you remember the construction, the general construction that Godon construction that contain these complex parameters. And now it turns out in order, if you want the Casimir operators for a particular channel, then you have to actually scale or send these inhomogeneities to some particular configuration into the set 0, 1, and infinity. So all of them have to somehow go to 3 points, just to 0, 1, or to infinity. And the way you do this depends on the channel that you choose. So in our work, we actually give a prescription for each channel. You can think of the channel as a plane moving tree, and then there's some kind of scale limit that you can take. So you introduce some indices n, some polynomials g and f for each plane rooted t, each channel, and then you take some kind of complicated construction, which is sort of a scale limit, and what you get out of it in the end is for each internal vertex of this tree, you get a function, well, higher order differential operator, family of higher order differential operators, Qth order differential operators, depending only on the spectral parameter. So the dependence, of course, now on the omega j is gone because we set that to some limiting configuration.
This is 4-point function.
This is for any number of functions. So what you can check is in this way. So you get like one family of operators here for each of these points, and you can check that the commutativity is of course not lost, so they will still commute, which is of course I think.
Where did the other guys go? I fix 0, 1, infinity, and I have.
No. Sorry. This is so first you fix. You can always fix 0, 1, and infinity, right? And then you take the other points and move them to 0, 1, or infinity.
Oh, so you are now at a singular point.
I'm a very singular point. Exactly.
So let's take 4 points.
Yes.
You approach 0, it's a perturbative regime.
Right.
You approach 0, you're sitting in singular point.
Right. Exactly. That's
Okay.
what I'm saying. So
Okay.
I have to go there, or I can go to 1.
Okay.
And whether I go to 0 or to 1, for instance, is the difference between S and T channel.
Okay.
Okay. So then there's a more general notion of how to do this for any kind of channel if you have this funny 6-point channel. So you can construct these sort of singular limits. And so one thing that you can then work out is, I mean, what you could worry about is, I mean, commutativity is not lost. You will still get families of commuting operators, but you could wonder that you maybe have lost some of your integrals of motion somehow in this context. But you can actually count that this is not the case. You have enough independent differential operators in that limit to as many as you have coordinates in your space. And so when you have these operators or families of higher order differential operators depending on omega, they actually have this form. They have some singularities and omega equals 0 and omega equal to 1, and the coefficients that stand in front of the singularities, these are concrete order Q differential operators, and you get in this way a family of very explicit, I mean, you can work them out explicitly, that's an expression a little long. You get a set of commuting differential operators of order Q that act on these wave functions. And among this set is in particular the Casimir operators, that's the terms, extreme terms. If there's only nu is equal to 0, so all the singularities sits here, or mu is equal to Q. These are sort of the Casimir operators, and in between you get some new operators, okay? So in this way, we have achieved abstractly this goal that I had set. So we now have a set of qth order differential operators. They all commute with each other. They contain the Casimir operators, and so we can look for joint eigenfunctions of these operators. Okay. And these joint eigenfunctions would in particular be eigenfunctions of all the Casimir equations, because the Casimir operators are part of this commuting family. So maybe just as an amusement before I look for concrete examples. So somehow this scale limit or degenerate limit of Boudon was not studied that much before. It turns out that so I think in some sense, in the more general case for arbitrary channels, our construction is sort of new. The only thing that was kind of studied before is the case of what is called comb channel, when you have like a plane rooted tree that looks like this without more complicated branching points. That's called in mathematics literature sometimes caterpillar limit. And actually, it appeared in very different work in the 90s of Kapowicz and Wilson, who studied an interesting dynamical system, which is called the bending flow system. And I don't know whether I should go through this, but it's just an amusing, simple construction. So it's a dynamical system that you can build, which is on the space of polygons in three-dimensional space, in RE3. And you take a bunch of vectors in 3 space that form a polygon, and you fix their length. So you have a set of real numbers that give the length of each of these things. And then you look at the space of all the polygons that you can build out of vectors of that length. Okay, and that turns out to be a configuration space. Well, or a phase space of this thing is, I mean, for each vector you have 2 degrees of freedom. They're sitting on a sphere, so you have n spheres, and then you have some constraints, so you get a 2 times n minus 6 dimensional phase space, basically. And you can actually introduce on this a Poisson bracket with symplectic form, just taking these standard symplectic form on the 2 sphere. And then what they notice is that if you take these diagonal mu's and take the square of that, this gives a complete set of a commuting set of Hamiltonians in this dynamical system. So that's called a bending flow dynamical system. It's a very cute construction, and in fact, it was noticed later that this is actually also a limit of the in this case SL2, SU2 Boudon model.
SL2C. Any SL2C works.
Of course, it works more generally. Later,
but for SLN, it's not know how to analyze that. If I take these things to be
to quantums.
Yeah. Take a group SLN, SL2C, yes.
Mm-hmm. Yeah. Okay. So anyway, I just wanted to show you this. I mean, so there is interesting integrable systems that come out of this limit construction, and some of them were studied before. The construction I presented on the previous slide sort of gives a larger set of similar systems, and I think the ones that are not related to this comp channel or caterpillar limit, they are actually new. All right. So now, okay. So let me summarize. So what I've tried to explain is that these building blocks that we believe we can use to evaluate these Witten diagrams for any number of points. These are wave functions of an integral system, namely of a Godon, a limit of Godon system. And I gave you sort of a concrete construction of all the differential equations. Now the question is, what do we know about solutions? And so in the last 5 minutes, I want to quickly sketch some of that, and this is now relating to previous work that I've talked here before. So the simplest case is if you have just 4 points, okay? If you have 4 points, then you well, okay, I will not give you the derivation.
It's my fault. It's my fault. I should not have jumped on you. You can continue where you want. Okay.
I will just give you the answer. So in that particular case, when you have a 4-point function, this integrable system, this limit of Godin model that I had for a conformal group G, is actually a very well known and very well studied integrable system. So you can actually show that this space of invariance that we talked about, and for 4 points, can be identified with the space of K spherical function, where K is just the SOD group, where SO1, 1 times SOD on the conformal group. So then you can take the Laplace operator on the conformal group and descend to the space of K spherical functions. And that is a calculation that long time ago Harishchandra has performed even universally for arbitrary spin. And you can compute these differential operators. In this case, there's 2 differential operators because you have 2 cross ratios. And in fact, you can do even without Harishchandra's work, you can do this computation quite easily, quite explicitly. You can just take the Laplace operator on the conformal group and descend to the space of K spherical functions. That's essentially a space that is K spherical functions depend on 2 sort of Cartan generators. And so what you will get is a second order differential operator. If you do that for the Laplace operator, second order operator on the 2 cross ratios, basically, that after a little bit of massaging takes this form. Okay, and that's a nice quantum mechanics problem. We basically have can think of it as 2 particles that move in 1 dimensions. The tau parameter is the coordinates of the 2 particles in 1 dimension, and then they experience this type of potential here, which is containing distinction cost terms, and then they also interact with this particular potential. And you can compute all these coupling constants of the parameters of potential, single particle potential, of the coupling constants between the 2 particles. You can relate that to the external dimensions of the field. So you can dial your weights, delta 1 to delta 4, and the dimension of space-time, and that gives you all these parameters in the potential. And so in this particular case, it turns out that the wave function that we're looking for, this psi of u and v, with delta 1 to delta 4 chosen, they are all eigenfunctions of this Hamiltonian. Okay, and so the eigenfunctions of this Hamiltonian provide a complete set labeled by this order, and then there's another 4th order operator similar to that. Those together specify completely a set of eigenfunctions which you can expand. So let me now say, so this is the case of this Sutherland. So sorry, I didn't say that. So this Hamiltonian, of course, has been studied a lot in the math literature. It's known as Sutherland Hamiltonian. It's a particular set of differential operators whose solution theory is actually very well known. If you did this construction before taking the limit, you just took the 4-side Godin model, as we Samson also recalled. That means you have 3 points at 0, 1, and infinity, but the 4th point is generic. Then this differential equation actually looks different. It's if you do it for SU2, you get something that's known as Hoyne equation, or more generally, you get some kind of elliptic BC2 Calogero-Suffolk integral. That's a much more complicated equation, for which the solution theory is much harder to do.
We solved it with Necros at that time.
Right.
We solved it.
Right.
Basically, for SU2, everything basically is doable. Question was we were not able to solve it for generic group.
I understand.
And you need generic group or SU2?
I need generic group. Yes.
And then it's completely over.
But so my point here is to say that fortunately, this is actually not the problem that we have to solve, but we only have to solve this general limit. And in that case, the elliptic model here goes to this trigonometric model, and that's much
Sorry, I can see what is not known is how to solve it with PDE methods. From the correspondence with gauge theory, we know the answer because it's given by super mills for any group, SUI, let's say SLN, whatever. So what is not doable is to look on the side as an integrable system, and so for SU2 we can check that the methods of integrable system matches the super Mills calculation or partition functions for certain limit. But that calculation is doable for any group. What we don't know is that it gives the right answer for, so basically it's a conjecture for higher groups. But for SU2 it's proven, I think.
Okay. So of course I need it for SO, which is always a little bit of complication.
Conjecture.
But
Conjectural formula.
again, I mean, my point is somehow that I actually don't need to solve this complicated problem. I disagree. The limits are actually okay. So let me try to wrap up. So there's actually another system. In fact, that I wanted to give you guys a challenge. When I told you about these vertex systems, that if you are in like a 4-dimensional theory and you have these vertex systems with like 2 symmetric traces, tensors, and 1 scalar, then you have some degrees of freedom sitting at this vertex, and you can actually also work out the corresponding Hamiltonian. And after lots of mapping, you can actually map that to a very exotic model that we found in the literature, was proposed 10 years ago, this linear-static elliptic Moser standard model. And for that, I'm not aware of solution, and of course, if you can solve that with these techniques.
That can be mapped to the whatever is called Zagor-Newton theories, and maybe.
Right.
I have not looked at those papers.
Right. Anyway, so that's one which has not been solved, would appear here. So let me just wrap up. So solution theory again is for this Calogero-Southern model is very well established. It's classic math, and you just look at this as a scattering problem. With this potential, you can work out the eigenfunctions. You can know everything about those eigenfunctions. So some kind of multivariate versions of hypergeometric functions, about which you can say pretty much as you know about the classic 19th century hypergeometric functions. As I pointed out, these vertex systems, that's a little different. For those, they remain elliptic systems even with this degenerate Godin limit, and so for those, I don't know.
So the Fender and other guys, I think, often wrote the Baxter equation for it, or I mean, spectral car. Did they give spectral car?
They didn't give spectral.
They didn't give that. So there is no description like Richiver had or the Conjure. No.
So I think this is an interesting problem. I mean, if that can be solved, then I think there's a very good chance that we can actually construct arbitrary solutions. And so one observation that we now talked a lot about, of course, this is basically now this Godin model is a higher rank integrable system, right? And so there should be something like separation of variable technology. To actually construct explicitly wave functions. So the separation of variables is supposed to give you all the wave functions as a product of what's called Baxter functions, and then some new separated variables coordinates. And if you had that, then you would have complete set of eigenfunctions. Okay. So of course, again, the problem is that the conformal group in D-dimension is a higher rank group, so you have to do this for higher rank, and that's something that there's a lot of development these days to extend that, but it's not done. But if you do this for the one-dimensional case, or the SO1, or SO2R, then actually you can obviously do this very explicitly. And so we know, of course, even in general case, even if we don't go to the general limit, we know the separation of variables. So we know the Baxter functions is solutions of some differential equation, which is this point equation or something extended, and we can build. So in that case, actually, the separated variables are just momentum. It's just a Fourier transform that brings you to separate the variable. And in general, if you're out of this special limit, then the Baxter function is a solution of the Hoyne equation or something, n particle version of that. But if you go to this degenerate limit, it turns out that the Baxter function becomes completely independent of the number of functions. It's always a Baxter function for 3-punctured system, which is just a hypergeometric function. So in that case, separation of variables the wave functions are just products of hypergeometric, ordinary hypergeometric functions, right? No dependence on n in this thing, just the only dependence on n is how many functions you have to multiply. Okay, so in that case, you can of course completely explicitly write down these wave functions.
Can I comment on this?
Yes.
Actually, that limit that you call generic limit when it takes last point to 0, 1,
Yeah.
or 50, and so on. This is called perturbative limit H theory. So the entire instantaneous sum is expansion in that fourth point. The infinite sum is the fourth point. So when you take that point to 0, let's say in a
Sorry, you're gonna take the fourth point to 0.
fourth point
Okay.
or 1,
Yes.
the same one.
Okay, okay.
Or to infinite. Doesn't
Yeah.
That's a perturbative limit, which means you
Okay.
just have to calculate perturbative part in the Armil theorem. Entire instanton complicated business is an expansion in that four point.
Okay, good.
So if you
Okay,
have
good. I see. So, but I mean, at least you have a
it's
sort
called
of different.
double Barth function. Double Barth function is a perturbative limit. And it gives an it's related to
The
this.
bar comes up, but yeah, I mean, anyway, we agree that this limit, I mean, a lot of the complications go away. It's a relatively simple.
Instantons are out.
Turns out, exactly. So, so if that, so again, this is a story about the rank 1 case. If you could do this for higher rank, then you would actually get sort of concrete formulas for these invariants for conformal groups. So that brings me to the end. So again, let's maybe to summarize this. Maybe I should actually go back to where we were in the beginning. So I told you that in order to compute these written diagrams, right, you can, all you have to do, so this is the written diagram, you have to actually know only these special conformal blocks, because this formula has very explicit simple coefficients, so expensive. So my whole discussion was about these objects. So we now identify these objects as wave function of the limit of Godin, a very special limit, and which this model simplifies a lot. So that means that we kind of know, so all the dependence on the cross ratios on the U's sits, of course, in these functions. So that dependence is completely fixed once you have constructed these wave functions. And then, of course, this is a formula really for this. So yeah, so that was sort of my main task. I told you that when you want to compute these strongly coupled correlation functions and strongly coupled conformal theories in the large n limit, the calculation boils down to essentially computing these wave functions. I think this is a manageable problem, even for higher rank. I think I'm now optimistic that one can actually get the concrete expression for these things. Also an interesting mathematical challenge, and that would then solve sort of the problem of computing these integrals. Now, let me conclude that the way we've done this, of course, any function that is a conformal invariant or any correlation function can be expanded in terms of these. In terms of this basis of wave functions, it's not always that the coefficients are so simple. So, in fact, you can use the same set of functions, of course, also in other contexts, not just to compute Feynman integrals, but also to do sort of to expand any correlation functions, even at coupling into these functions, and then try to self-consistently determine the coefficient. That's known as conformal bootstrap programming. And in this context, I should maybe mention just very briefly that there's an interesting limit when you can take these wave functions, and this I don't know so well how it's incorporated in this integral systems language, but in physics it means that you take these x points and make them light-like separated. And it turns out that in this limit the differential equations simplify drastically, so they are highly coupled, of course, non-separated for a generic limit. But if you take sufficiently many points sort of light-like separated, it turns out that these differential equations separate without separation of variables in some sense. You can actually write down explicit solutions, and we've used that recently to study sort of conformal field theories through what's called the light cone or analytic bootstrap which is just another application of this this type of technology that I try to explain beyond computing these written diagrams. Okay, good. So let me finish here.
Any questions, please? I won't be asking anymore. I have so many questions. Other questions, please?
The separation of diagrams, separation of variables. So I guess, I mean, like I know Go and
Yeah,
so it's this stuff, but it's always SU in that case, right?
So it's SU, so the SO is a bit, so of course, if you do four-dimensional conformal field theory, then fortunately SO is the same as SU2, so then you can use this this technology. In general, of course, you would have to extend it to the SO case. So yeah, I mean, this is some ongoing work now with subset of these various teams working on hiring the separation of variables, trying to put this machinery in place to actually compute this.
And there, yeah, the compact non-compactness thing just matters. You're always
Well, I mean, they do work a lot for non-compactness.
do they?
In these groups because they have,
Okay, I guess the thing is, I thought I know they did like SU3 and so on, but I didn't know they had managed to get say full. I don't know. Okay,
So I mean, it's
they have.
also on their side, but I mean, they study also sort of the non-compact problems.
Didn't Eva do like GLN for?
Okay. Yes.
Any other questions, please? Sorry.
I think I can ask this. All the integrable conformal Feynman integrals I know about are ones that are invariant in the conformal Yangian. So these are different class of integrals. They're not.
Yeah, I
easy
can't
things.
really place that into the same
story.
context. I mean,
Yeah.
So yeah, there's of course a lot of integrability also, in particular in perturbative weak coupling calculations. I guess that's what you're referring to. And so integrability seems to be around in many places when you do these calculations. This story that I presented here was mostly a story for the strong coupling expansion, because somehow it seems that this particular wave function of this integral systems are particularly well suited to expand answers at strong coupling, because the coefficients become so extremely simple in strong coupling. But there's probably something that.
Yeah. Okay. So you haven't thought of it in relation to conformal Yangian.
No, I haven't.
So I guess in some sense the integrals you're looking at are sort of like in flat space, right?
Yeah.
So I mean, usually it's quite difficult, but is there any possibility of taking a flat space limit on these things?
I haven't really thought about it.
Yes. I mean, it's usually difficult. Maybe go down.
Oh, it would be fun to think about.
There actually was one paper about
Yeah.
Yangian symmetry of these ADS Witten diagrams. So it was some group in America. I don't know. I actually don't know who they were, but yeah. It was an unexpected kind of paper to appear.
Okay, I would be interested to.
Any other questions, please? If not, let's thank Volker once.